Consider a quantum particle on a unit circle. On a unit circle, the position of the particle can be labeled by the angle theta. So this is our unit circle, and along this circle we have this angle theta, which goes from 0 to 2 pi, and this angle can be used to label the position of the particle. So we can define our position operator x in the usual way as a product operator, which acts on any function f as multiplication operator by variable theta. And we can define our momentum operator as partial derivative with respect to theta with factor minus IH bar. So these are our position and momentum operators. Now it is easy to see that these operators satisfy the usual commutation relations. If we take commutator of x with p, then it will be equal to IH bar. So this commutation relation holds. However, if we take these spatial states psi and theta, these are eigenstates of the momentum operator with eigenvalue nh bar. So these psi and theta for n integer, so n is integer, these are eigenstates of the momentum operator with eigenvalue nh bar. In any such state psi and theta for any fixed n, the uncertainty in momentum is of course 0, because these are eigenstates of the momentum. So uncertainty in momentum is 0. The value of the momentum operator is a fixed number in any of its eigenstate. So the uncertainty in momentum is 0. Also, if we take uncertainty in position operator, then since position can take values only from 0 to 2 pi, so it will be some finite number. Therefore, if we take the product of uncertainty in position with uncertainty in momentum, then it will be 0 for these eigenstates of momentum operator. This implies that the Heisenberg uncertainty principle is violated in these momentum eigenstates in state psi n for any integer n. So Heisenberg uncertainty principle is violated on the circle for these momentum eigenstates. So why is this so? Why is Heisenberg uncertainty principle is violated on a circle for these momentum eigenstates? The reason is that in the derivation of Heisenberg uncertainty principle, one makes use of this commutation relation. This commutation relation says that the product of this product operator x p minus product operator px is equal to I h bar, where there is also an identity operator implicit in this equation. So this is what commutation relation says, and this commutation relation is used in the derivation of Heisenberg uncertainty principle. However, this commutation relation is valid only for those states where both of these product operators xp as well as px are well defined. So this makes sense only when both of these product operators are well defined. However, if we take these states psi n, and if we consider this product operator px, and if we act this product operator on state psi n, then we'll get this x operator will act on psi n and it will multiply it by this parameter theta, and then we'll act this product function theta psi n with momentum operator p. However, you can see that this theta introduces a jump discontinuity in this function psi n at theta equal to 0. Therefore, this product function is not differentiable. This is not differentiable at theta equal to 0. Therefore, this product operator px is not defined for these states. So since the product operator is this px is not defined, therefore this commutation relation also is not valid for these states. And since this commutation relation is used in the derivation of Heisenberg uncertainty principle, the Heisenberg uncertainty principle is also not valid for these momentum eigenstates. So this is a very peculiar example in quantum mechanics where this Heisenberg uncertainty principle is violated.